Hello students, welcome back to the session of Digital System Design using Verilog STL. This is session 2 and today we are going to discuss about the detailed structure of hardware description language. So what is hardware description language? It is a computer-based language that describes hardware in text form. It can be compared with other programming languages like C. But the difference we have to remember is that C is a software language and what we are talking about is a hardware language. It is used to describe the logic gates, truth tables and Boolean expressions in general. So what exactly we are going to do in this? The ultimate task is to make a controller, processor or an IC. What is there in a particular IC? In a particular IC, there are various structures. For example, we may use arithmetic logic unit in a processor. So we have to design ALU. We have to use memory devices. We need various register files. We have other control units. And all of them are made by using digital circuit components. So we have to design this particular processor, that is nothing but hardware description language, and this will be mounted on an IC. So what exactly we are talking about? The basic element, the most basic element in any electronic gadget circuit is transistor, and we use them for on and off. On means logic 1, off means logic 0. It's all about digital. Digital rotates between 1 and zeros only. So let us see the flow, how we get. At the basic, we have transistor. We can have various gates by using transistor. For example, this particular circuit is for inverter, that is NOT gate. That means if input is 0, output should be 1. If input is 1, output should be 0. This is one kind of gate. Like that, we can create a design for multiple gates. So we can have a structure of a digital logic design where we will create various gates. And at the core of gates are nothing but made up of transistors. Now these small elements will be part of a big circuit. Say complete a processing unit. And these things we have to mount on an IC. So this is the journey from transistor to IC. What is role of HDL? Hardware description language will design this structure, what exactly will make that processor work the way he want to, the way he is supposed to work. And what are the other software programming languages? If we have a laptop, if we have a computer, once the processor is ready, then that processor can run other languages like C language, Java or any other language. But who is making processor? Processor is made by using hardware description language. It is very high-end language which is defining the processor. And that processor or controller is heart of any system who will tell other softwares to work. So if you might remember the operation of simple inverter, if inverter input is 1, what is expected output? It should be 0. But how exactly it works? When input is 1, the top transistor will be PMOS and the bottom one will be NMOS. PMOS is also called as pull-up. We have pull-up and pull-down transistor. When supply is connected and input is 1, this input 1 will force this PMOS to become off. So when input is 1, this PMOS will become off. When it is off, there is no path between VDD to output. So output will be 0 at that time. It's like this. So we have switches. One transistor will work as one switch. So if input is 1, PMOS will be off and output will be 0. This is how it works. We have only ones and zeros. According to our logic and design, the circuit will perform. Then what are the advantages of hardware description language? It allows the designer to decide everything before the manufacturing of the actual hardware. Before manufacturing of IC in the company, we have to decide what will be the output of that particular IC or microprocessor or microcontroller. We can make decisions about cost. We can make it cost effective by making a proper design of that particular IC. We can decide the power and the area. What is the most important parameter nowadays? Area. We have to scale down the area. We need more functions in less space. We want everything in pocket with less space, all the functions, more functions. That's why the VLSI technology is increasing, where number of transistors are increasing on a single chip, but the size is decreasing. We are having smaller and smaller processor with millions and billions of transistors mounted on that. And who will design that mounting of transistor? An HDL engineer. Now let us discuss types of HDL. There are two types of HDLs. One is VHDL and another one is Verilog. In VHDL, HDL stands for Hardware Description Language and V stands for VHSIC. What is VHSIC? It stands for Very High Speed Integrated Circuit. That means we have very high level of integrated components on a particular chip, and this one was developed by the US Department of Defense. Initially it was developed for some military operation. Then next one is Verilog HDL. It is developed by Cadence. Actually they also bought it from some other earlier version in around 80s. Someone had prepared some software called Hilo, and from that they got an idea and they prepared Verilog. We will see brief history about say VHDL. In VHDL, first they developed it on the request of US Department of Defense. They used to create some applications which were used in military. So those specific applications were using ASICs. In last session we have discussed what is ASIC. ASIC is application specific integrated circuits. If I have a specific task, then I will not use a general purpose processor. I will design a specific IC which will be used for my specific function, not for all. For example, if I have a microprocessor which can be used for a wide range of applications like processing the data using internet, printing, input-output devices and much more. But if I want to design some particular function where I want to take only one part of that processing work, for example, working on a washing machine will have a fixed kind of operations. So for that fixed kind of operation, I can design a separate IC. I don't need a high-end microprocessor. It will waste the resources. So I will prepare a microcontroller which suits that particular condition. So if I am creating some IC which is application specific, I will call it as ASICs. So what US Department of Defense did, they had some project, and they had few projects, and for that they required application specific ICs. They received it from the manufacturers, but they wanted to check the ASICs, how they work and how they get the information. So they created the logic simulators that could read the VHDL files of the ASICs, and after that there were logic synthesis tools which can read the VHDL and convert it into the logic gate level. So that's how VHDL started. Along with VHDL, another popular HDL is Verilog. Let us compare them. Both of them are HDL's hardware description language, and one software consists of if you take one software, for example, Xilinx is most commonly used nowadays. Xilinx Viodo is the version which people are using, but the size of this software is much larger, say from 12 to 15 GB around. We need the space to install that software, but it contains both VHDL and Verilog. We can select in which particular mode we want to program, but the programming syntax and the programming style is different. For example, VHDL use entities to define the architecture. In Verilog, we use modules. So that is one difference. Otherwise, both of them use gate level data flow and behavioral modeling, and both have synthesizable subsets. This is about VHDL and Verilog, but we are going to use Verilog in this subject. This subject specifically focus on the Verilog. By using Verilog, we can describe one single flip-flop, or we can have a design of 1 million gates that we can make in the form of text, and we can simulate it, we can synthesize it, and we can check how exactly it will look on the IC. So that's what we are going to do. Let us have a brief history about Verilog. Before that, I would suggest you to take this subject seriously, because a lot of job opportunities are there in this field, right, in the India as well as and in US also. Verilog is used very widely. You can have various jobs, various posts in this particular course, like digital design engineer, ASIC design engineer, FPGA. There are a lot of possibilities in this particular core branch. So I suggest you to learn Verilog as well as VHDL. Any one is also enough. For Verilog, there are a lot of job opportunities. In today's quiz, you have to answer. First question will be related to job opportunities using Verilog. You have to list the job opportunities using Verilog in the comments as answer of question 1. You can also explore on internet which countries are offering core jobs of VLSI Verilog based software. So now let us see brief history of Verilog. The company called Gateway Design Automation, they first started the idea of Verilog, and they developed some module. They copied it from some other popular software of that time, and later on in 1900, Cadence company, it is very famous company which developed various FPGAs and CDMAs and the tools related to HDL. They purchased the Gateway products along with the company Gateway Design Automation, and after purchasing that, they developed the software of Verilog, and they gave it for more open platform to discuss it, like in Open Verilog International. And in 1991, they gave the documentation of this hardware description language, and it was open till after that. Earlier it was closed. That means they had not disclosed how it works and what is the documentation and what is the basis. But once it was open, they found that there is a threat of more modifications in their basic idea. So what these people did, they started process of making it a standard, and they approached IEEE, and then they had a committee and they passed it as an IEEE standard. So Verilog is now an IEEE standard. The components, the syntaxes and the programming, everything is defined under IEEE standard. Now, what are the design methodologies or design styles in Verilog? How we can design? So there are two approaches. For anything what we want to design, we can use two approaches. One is bottom up design. In that, what we will do, first we will start with a small component, and then we will move to next level and then to the top level. This one is useful if our system is simple and small. For example, if you want to make a full adder, so first you will not start with the block diagram of full adder. First you will start on the gate level. First you will connect the gates, and you will see the functionality of gates. You will use the required gate which can make a full adder. Then those gates, XOR gate, AND gate, you will use, and you will design it, and then you will make, say, 2 half adders in the second level. First you will take the gates, say you will make 2 half adders. At second level you will add 2 half adders to get the full adder. This is bottom up design. That means you are starting from the basic element, right from the transistor and gates. But it is useful if your system is small. But if you have a large architecture, then you can choose another style, like top-down design. First you will make the block diagram. I will make a block diagram of, say, full adder. I want a full adder. In full adder, I need this number of inputs and there are this number of outputs. This is my block diagram. Then how I will make? Then I will decide, okay, for making one full adder, I can subdivide it into 2 blocks of 2 half adders. Okay, I have to combine 2 half adders. Then how I will make 1 half adder? I require these gates for making 1 half adder. Then I will go to the bottom level. But in many times we cannot rely only on one type of methodology. We can use both bottom up design, top down design, because if system is larger, we require both approaches, because some particular part may be useful for a particular design methodology. When you work in a team, a complete project may be divided between various team members and everyone will complete his task. Say one person is making half adder, another person is making ALU, another one person is making some memory component, and at the end the leader will combine all these designs into one particular project. That's how it works. So in top down design, if we consider an IC, so ultimate task is, say, to make IC. So for making IC, first we will have the specification that I want this IC and this IC should work in this way. In this way it should be used in this particular application, or in medical field, or in military field, or it is a general purpose processor. First I will have my specification. Then I will make high level design, like the block diagram, the big picture. Then I will go to low level design, like full adder I am dividing into 2 half adder. Then I will check for the resistor transistor logic. We can have this coding. Then we will verify the functions. Then we will have logic synthesis. In that we will do logic gate level simulation. If this simulation is working or not according to its input, again we may go back to the previous stages wherever required. Once our design is fixed, then what we have to do? We have to place and route it. We have a silicon. We take silicon from nature, say, and then we purify it. Then we will make a base material. Say one base we are making P-type. And on that we have to place and route. That means I have a design. I want it on an IC. On this IC I want to place my design. So I will place it on it and I will give the roots. Once it is perfect, then we will go for the fabrication. And once fabrication is done, again we have to validate it. We have to check sample ICs whether they are doing the desired operation or not. This is how top-down design model works. What are the Verilog abstraction levels? We can have 3 levels. One is behavioral level. We can check the behavioral level. Then we can have the register transfer level and gate level. So briefly discuss what are these things. In behavioral level, it describes the system by concurrent algorithms. Like each algorithm itself is a sequential. That means it consists of a set of instructions that are executed one after the other. This is in the behavioral level. Then in register transfer level, what happens? The designs who uses register transfer level specify the characteristic of a circuit by the operation and the transfer of data between the registers. Right? For this purpose, a separate clock is used. The RTL designs contains the exact timing. The timing is very important in this particular session. And then next, the bottom level, the most bottom level is gate level. What happens in gate level? Within the logic level, the characteristics of a systems are described by logical links and their timing properties. But the gates will have a definite logical value. Either it will be 0, 1, X or Z. So these are called as like predefined primitives. Like in any language, there will be some predefined keywords. These are called as logic primitives. These are like AND gate, NOR gate, NOT gate. These are called as primitives. They are predefined in this particular language because everything will be built on the gates. Second important topic is what is logic synthesis. In simple way, logic synthesis is a process of converting high level description into optimized gate level representation. We have a description in text format, we may have a description in written format, and we have to convert it. We have to check it how exactly it is looking on a gate level. Then in turns we can decide the design on an IC where transistors will be mounted, transistors boundaries will be defined, and we will have fabrication process. And they use some standard cell library like we have discussed about the logic gates. So we require logic gates, we require muxes, memories, flip-flops. All these things are part of a processor. We require them in some kind of standard library. And the technologies what we built, we process, manufacture, they are known with the size of transistor. Say I'm using 0.18 micro technology or 90 nanometer technology, like that. So in synthesis, other than these gates, we can have bit stream of PLAs. So PLAs, PALs, FPGAs, or when we want to target ASIC, so they can have some EDA kind of stuff, electronic design automation. For that we have synthesis tools that we will see in the programming. So what we have to do as a designer, first we have to understand the architectural description. What is the description, architectural description of our program is. Then we have to consider the constraints, the timing, area, testability and power. Power consumption is also very important parameter. Area is also very important parameter, and timing synchronization is also very important parameter that we will discuss about clock in some time. Power, we have to use less power and give more output. Okay, what is in synthesis we will see in short. We have HTL code, we will create a code, we will use the technical library. These two things will be required by synthesis tool, and what he will do, this text form and the use library definition, he will convert it into gate level, and he will tell us, okay, this is looking like this. I'm writing a text on a paper, I have programming, I have a complete set of instructions in text form, but how exactly it looks on gate level? For that we require synthesis. We call this process as synthesis. It will convert it into a netlist, that is in the form of gates, right? So by using synthesis tools we can optimize the design as a whole. Now there are very famous synthesis tools, like the various companies they are creating it. Mentor Graphics, Synopsys, Cadence, we are most commonly using Cadence, Altera and Xilinx, and they are having some design environment. There are names like Xilinx design environment is called as ISE. Xilinx is used in our labs, and as we are working from home and due to lockdown we are at home, I don't think everyone will be able to download Xilinx, because Xilinx have a huge size, say from 12 GB to 15 GB. But surely I will come with some solution so that we can practice the program, because this subject is more about practicing the programming. So for that we will see what we can do. In next question you have to second question in comments you have to answer is the tools names. What are the various tools we are using for HTL as described in the previous slide. Now let us compare it. Again, we have to remember one thing, that HTL is not a software programming language. It is a hardware description language. So description means it is a written text. We are describing it. I am describing it in a written text, and it is meant for a particular design on gate level. This may be part of a wider IC or processor, right? And what is software programming language? It uses machine instructions, but it is executed on a computer. Here, computer will run the software, and what we are doing, we are creating a computer. That is the processor. Now, and another main thing, while programming, there are differences in programming, that like in C, we start our program with some particular beginning, that is say main. We start our program with main, and then one by one we go to the next instruction. But hardware doesn't work like that. Once it is on, everything should be on. That means everything must active at once. I cannot say that, okay, first my one IC, one application is active, first my RAM is active, after that ROM is getting activated, and then CPU is working. Like that it cannot work. Hardware must be active all at once. Not like software program where executions are done sequentially in line one by one. So two main roles of HTL and related tools are, like, first, we have to specify the digital logic. We have to have a design, and it must be appeared for implementing our final design. For that we use synthesis, and then simulating and testing a design. Let us check difference between synthesis and simulation. Simulation is nothing but error finding. Like when we say I am simulating my program, that means I am checking the errors. If there are errors in my written code, right? If errors are there, we will rectify it, we will remove it, and again simulate it, we will remove the errors. And what is synthesis? Synthesis will give us a pictorial form of our written text program. Say if I am writing A dot B is equal to C, then it should show us AND gate. This is what you are typing. This is what we are doing in synthesis. So this is the difference between synthesis and simulation. Timing is very important here. We must have synchronization, and synchronization, like a clock. What clock do? It will have a synchronization between hour needle, minute needle, and second needle. So these three needles work together. If they don't have synchronization with each other, what will happen? The time will collapse. We will not get the time. So everything must be synchronized. Inputs are changing. Maybe they are changing rapidly in terms of zeros and ones. We must consider the delays, and entire circuit timing must be synchronized. So that output must change with respect to change in the input. Otherwise, what will happen? We'll get glitches. There will be errors if timing is not matched. That is why the synchronous system should have minimum clock period. Okay, this is about timing. Combinational logic and sequential logic circuits, we have to use their differences. Again, we will discuss in coming classes. There will be 2 more questions given along with these 2 questions asked in this video. 2 questions will be given based on the previous question asked in examination. The previous question paper will be shared along with this video, and the next session we will discuss about the parameters, which the syntaxes and other things which we require to understand this language. Till then, have a good day.